Hey, good evening, Anish.
Hi. Hold on. Thanks for joining. Hold on. Let me stop recording now.
So let me know when you guys are able to. So is the screen shared?
It is available. Thank
Oh,
you, Himanshu. Go
okay.
ahead, please.
Thank you. Thanks, Ganeshan, for inviting me for this talk, and privilege and honor to be here to share about my experiences in my journey towards using open source products in my personal capability and also a bit in professionally also. And thanks for that. And I hope everybody is doing fine amid this COVID, so everybody stay safe. And yes, the talk which I wanted to give, because considering the audience is about cloud native, and then sort of about a little bit talk about OpenShift, because this being a forum for open power, so it is sort of wanted to give an open source angle to it and discuss about what is there in the open source space for as far as cloud goes when it comes to enterprise implementing the cloud. Brief introduction about myself. Yeah, so I call myself as an open source consumer, not much of a contributor, but yes, I consume a lot of open source technologies in my as a hobby and my work also. I have basically experience in high performance computing. I have been doing workload scheduling for quite a few time, and from working in distributed computing, high performance computing, I think it was a logical progression for my career to move towards cloud. And yes, in that respect, as past 4 or 5 years has been quite fulfilling, as the cloud has bloomed like anything. So I have been fortunate enough to be the part of that cloud journey, which I started in 5 years. Uh, Apart from my work, which I do in cloud space, my interests are in physics, and that led me to my interest in quantum computing. I've given a couple of talks on quantum computing, and I used for the demo IBM IBM Q the experience that computer to give the demo of the basic 5-qubit quantum computer. Uh, Apart from my interest, yeah, I am a certified mountaineer and a rock climber. And the picture which I've shown you here is generally when for my talks, I give the picture I put is past 6 months. If I have done any adventure, I just post it. This picture is quite old because of COVID. It is 9 months old. So hopefully when this situation will be over, I will have a new picture here. So this is my expedition towards a 20,000 feet peak, and it's while coming back from that. And you can reach to me at Cloudhar on Twitter and Cloudhar at GitHub. Okay. Uh, no, the agenda about this meeting. So basically, I just give a context here. So when I talk to my daughter and I ask her what's her favorite subject, and the subject comes science. Why science? Because the teachers are good at teaching, and the experiments which they do, it looks magic for them. She's in 7th grade, and when I say what subject she hates, and it's the history. Reason being, yeah, it's the teachers are not maybe that communicating that well the history, and that has led to her not much interest in history. But I believe history is a very important part because it helps us get the present context of things, why things in present are so. It's because of the history behind it. Like the future technologies are dependent on what are the work which we are doing currently, and in the same way, whatever technologies we are using currently are dependent on whatever the work was done in the past. So it's necessary for us to know about the history of that also, because that will give more meaning to a lot of things which we are doing currently. So this talk is mostly focused on first to give you a historical context of the cloud, even though cloud was quite early, but what triggered the cloud to become like in those 4 or 5 years to be what cloud is. So give a historical context of it. So so that you the present context you will be able to appreciate it much. Second, I wanted to also talk about what are the two driving factors which have made cloud a priority for enterprises, startups, all organizations to go to the cloud, and what are the contributing factors which have hastened the pace of going to the cloud. Then I'm going to talk about what are the ways now for us to go to the cloud. Like I'm a new enterprise, or I am a, let's say I'm a student, like this is a mostly a student forum. So I want to get started with the cloud. So how should I get started? It's applicable for a startup, to an enterprise, and also for the students to find like what is to be a cloud journey. How should we go about when it comes to getting onboarded to make yourself cloud native and work with the cloud. And I'll talk about various technologies which are the part of the cloud landscape, and try to build a sample app, what are the components needed to it, and conclude with an OpenShift. So that is talk about history, talk about driving factors, talk about how to get yourself onboarded to the cloud, and then conclude with OpenShift. So that is the structure which I am following here. And this is agenda: talk about deployment models, talk about cloud history, then Kubernetes and CNCF, Trailmat, native landscape, and then I'll talk about OpenShift. Okay. Okay, so since a lot of people might be sort of, because this wanted to give an introduction to OpenShift, that's why I wanted to give a basic background of a deployment model. So how the deployment of the software used to be, and so it's a precursor to the things which will come forward, and so if you see, like I'm not that old, but yes, I started my career in early 2000. But if you see what kind of deployment models in an enterprise and industry was, it was, we used to call it a traditional deployment, because what basically it used to happen is, so earlier organizations, they used to basically run their applications on the physical servers. So there was a physical, so basically if there was no way for you for us to define boundaries. So if you see, you have a hardware, on the top of hardware you have an operating system and you run applications. Now straightly you will feel that yes, there are problems to it. For example, if you see application 1, it might consume most of the resources of the underlying hardware, and the application 2, which is somewhere becoming critical, it will not get those resources. That is one, like resource crunch you will straightly see in this traditional kind of deployment. Another issue with this kind of a deployment was security. Like an application 1 might be having some bug which might lead to crashing of operating system, and this might get the application, other application will also go down. So this was a problem. And how we used to avoid it? Basically, one app per hardware. So deploy a single application on a single hardware. If you require to deploy another application, bring on another hardware, deploy on that. So that is how we actually achieve the segregation, security. But immediately the problem was, if you had one application per hardware, per physical box, the utilization went on a toss. But yes, we had to live with it. That was what best was available, and that was what we were doing at the time. Okay, so this is traditional deployment, and then we move to something called as virtualized deployment. And as I mentioned, the resource utilization in traditional deployment was a pain, and virtualization sort of addressed that. How virtualization addressed is, it allowed us to run multiple operating systems on a single hardware. Now, how it did is, basically this virtualization environment, what it did is, it emulated the hardware in software. So it made a software copy of hardware. It made software cores as a software construct, memory as a software construct. Now you cannot divide hardware, but you certainly can divide software. So now, as the cores and the memory and the resources were a software construct, you could divide those into different logical chunks and assign each logical chunk to each an operating system. Now, the operating system running on top of hypervisors, it's thought that it's the one which owns the hardware, where it was not the case. So what happens is every operating system is thinking that it owns the hardware, it owns the underlying resources. So what you could do is you could run multiple operating systems inside a single hardware. Now what happened? It helped us in a better utilization, because now you could pack more of virtual machines inside a single physical deployment. Yeah, so there was a sort of side construct to it is because the operating system, so each application should have, so you will run multiple operating systems inside on a physical hardware, but that gave you one fault tolerance. Security concerns were segregated because you ran application in their separate operating system, plus you did a better utilization of the resources. It was good, but the only issue, one of the issue was still even the virtual machine was a software construct, but it was not portable. Like if you have to port it and move it to some other thing, you have to actually 5 gigs because it was operating system with it. So basically, virtual machine, even though it was a software construct, but it didn't allow you much of a portability and deployment. But it solved your main problem, which was utilization and isolation at the software level. And come the latest development which happened is the container deployment. Now, container deployment is like a virtualized deployment. But one thing is, in virtualized environment, you had every application deployed in its own operating system. So you have multiple operating systems running on a hardware. But here, what's happening is the operating system is shared. Now, only those components of the operating system which cannot be shared, they become the part of an application. To give an example, file system is one. Which cannot be shared because every application will have its own file system to write and they want to maintain it. Second is CPU, memory. So those things were segregated and they were made part of the application and the binaries and libraries, and rest shared operating system was found. So how did it help? It helped to make the size of that application coupled with its binary smaller, and that came to be called as container. And the beauty about this was that this was a smaller application containing library which you could basically deploy easily. You could port it, you could make it because of small size, it could be deployed quickly, it could be ported, it could be run. So that application combined with the binaries which is required and libraries which is required to run that application used to be called as a container. And the container is a lightweight version of what you can saw in IBM. And how does it help is, containers also give you resource isolation. So if you see that this container should run only this much of CPU memory, so it is constrained to run in that whatever is allotted to you. And how does it help? Now you can do bin packing. You can pack multiple containers on a single host, on a single operating system, and you can run. And that gives you better utilization. Plus, it also sort of gave the origin of DevOps culture. Is development, and earlier if you see before container, development and operations were sort of combined. So there was always tussle going on between development and operations. Development wanted to release faster, but operation doesn't want to break things, so they wanted to release very slowly. So there was always like who wins it, and but with the container, because you could code your application along with your binary, a developer could basically build and release its application quickly, which doesn't have to be dependent on the deployment. Deployment can happen separately, but build and release can happen separately. So this containerization gave the world, gave the technologists and us a mechanism of a DevOps culture, wherein the agility increased, development happened parallelly, deployment, and there were no way there was a hard binding between the two. And the development and operations could sort of work parallelly on their things. So this is about, so you see the transition. What has happened is we have moved from sort of physical boxes to containers, and now you see what is happening is as earlier there was a single big application resource, and now you have small containers. Like it's in the modern terminology you would call them as pet versus cattle. So now containers are called cattle, in the sense is even if your container dies, you can spawn multiple containers, you can run them, and that analogy of pet, where you have to be concentrated on that application, is no longer there. You can spawn the containers at your will, even if you can destroy at your will. If it gets destroyed, it will get spawned again, and that way the fault tolerance on the application is also achieved. Okay. So now that you have the context of physical hardware to virtualize, so to the now, which is container. So I wanted to give you the journey of the cloud. How has it happened over the past few years? Let's say 2 decades now. And the journey started in 2000, and Sun was sort of at that time commodity pioneer, and at that time, like if you have to basically, it was again that traditional deployment. If you have to buy a new server, if you have to new application, buy a new server and put that application on the server. If you have multiple applications, buy a rack which consists of multiple servers and put your application. So that was the way in early 2000 we used to do. It's non-virtualized hardware, and I believe now we have a pretty context because we discussed it in early. Now, in 2001 was the year when virtualization came into market, and this was released by VMware. And as discussed, it allowed better utilization, but because now you are able to run multiple operating systems on a single physical hardware, giving you better utilization and better security, better sort of fault tolerance also. 2006 was the time when AWS came into picture, and AWS didn't coin, but AWS the term of IaaS came into picture with AWS. When I say IaaS means infrastructure as a service. What it refers to basically is infrastructure resources, the cloud infrastructures that are delivered to the organization via virtualization technology. Means I, as a organized enterprise, I will use infrastructure which is sort of hosted by AWS as a service. When I say service, is that I will only consume it when I require, and if I don't require it, I will not pay for it. So that IaaS concept came in 2006, and EC2 on Amazon is a prime example of it, which is infrastructure as service, wherein the hosted environment is not in our own enterprise in our location, but the infrastructure is hosted by a cloud provider, and we just use it through the internet. And it has changed the paradigm that from CapEx, capital expenditure, which we are doing at our end, now we have moved to OpEx kind of infrastructure, and now we don't more need to have infrastructure at our own place. And this was a game changer when it came to cloud. Okay, moving to 2009. Now, 2006 was infrastructure as service, and when we moved to 2009, platform as a service. Now, what's platform as a service? And as I mentioned, infrastructure as service is basically wherein you use infrastructure and then you basically did what you have to done on top of it, with operating system, everything. But platform as a service is a cloud computing model in which a third party, in this case the cloud provider, delivers both hardware and software tools which are needed for application development. Means I am a big basket. I know my application of selling the vegetables. I know that I'm good at that code. So I don't need to worry about the hardware. I don't need to worry about the infrastructure. I don't need to worry about operating system. I don't need to worry about the database. I don't need to worry about the middleware. I just need to worry about my application, and the PaaS platform will provide me all of those things, which will help hardware, operating system, as well as those tools. And I need to just go there, put my application there, and boom, I'm running. So platform as a service was a sort of a game changer, developed by sort of Europe in 2009, and it was as simple as if I assume that people are doing working with JIT, just like you push your code in JIT and you do JIT push master. In Heroku, if you have your own code, you do JIT push Heroku, and what will happen is your code will get deployed on the Heroku PaaS infrastructure, and boom, the application will be up and running. It was so simple. And at the back end, the early sort of containers and those were running, and they used to sort of help in the deployment. But yes, this was a game changer wherein we moved from infrastructure as a service to platform as a service. And I, as an application developer, need only to worry about my code. And 2010 was when VMware was a proprietary VMware technology, the virtualization technology. And 2010, OpenStack, along with other enterprise organizations, came together, and they formed the open source version of virtualization, and which was coined as a OpenStack. And OpenStack enabled everybody to create their own private cloud infrastructure, IaaS infrastructure. And it's still being used, predominantly being used in telecom industries these days. 2001 was what happened to 2001 to 2010. 2011 was open source PaaS. Heroku 9000 was a proprietary PaaS. Cloud Foundry open source the PaaS, and that again changed the game. It was a game changer. IBM's Bluemix is a prime example. It's based upon open source Cloud Foundry, and now the PaaS solutions became open source, and a lot of projects took up from this the Cloud Foundry of 2001. And 2013 was when Docker came into scene, and Docker has, what I've read is Docker has the fastest uptake among developers. So it was a technology which was sort of accepted by developers with open arms, and the rate at which the developers have accepted the Docker technology is fastest than any of the other technologies which has come all along in the development environment. And Docker, again, Docker is what we placed a slide, it was the container. And 2015 saw the advent of Kubernetes and Cloud Native Foundation. And this was a game changer in terms of what led to sort of a development of how the cloud is in shape today. And Kubernetes and Cloud Native Foundation are the two primary drivers, which in my I think are the ones who have actually shaped how the cloud is in the current form, and they are sort of a main driver in the future direction of the cloud will go. Okay. So, about Kubernetes, so why Kubernetes was a game changer? Now, basically, if I say that we saw that containerization is a key. So you containerize your application with the container. Basically, you can have a consistent, repeatable deployment on a wide variety of systems. But the issue with this is if one or two containers running, it's okay. But when it comes to running containers, multiple containers scale, it becomes a big pain. Now, for example, if you're running a container and then suppose container dies, then you have to SSH into that node and see if the container had died, then restart that container. Now you are trying to sort of got an information that container is not running, and then suddenly the SSH connection died, so you will not be able to SSH into the machine. Now you also need to have sort of monitoring and all those things plumbing in place so that you basically are able to monitor those hosts which are running your container and then sort of take an action. So in all, one container running or two container running is okay, but running a container at scale and enterprise is a very challenging task. And people tried using their scripts, people tried to write their own systems, monitoring systems, sort of club together a lot of scripts together to make sort of containers run properly, like if container dies, respawn the container, take actions, but it was a humongous job. And that is where the Kubernetes came into picture. And what Kubernetes is, it is a container orchestration tool. Basically, small definition, its aim is to provide platform for deploying, scaling, and operations of your containers on the host. So now that you have containers, if you have to an enterprise, you run thousands and even millions of containers, and what Google does is the container orchestrator will keep track of those things, where it will manage the life cycle of the container. It will respawn the container if the container redies. It will make sure that your containers, whatever you have asked, it will monitor them. It will do the health check. So all of these things of running your containers in scale in enterprise, container will be able to do. Kubernetes will be able to do. Now, why is that important? Quickly, Kelsey Hightower, in one of his 2017 keynotes, he mentioned that Kubernetes is the Linux of the cloud. Now, it's a very important comment he made, and it's very true also. Because if you see Linux, the Linux kernel will help you run the application on a single physical host. But when you have to run your application on a cloud environment, and when you are, if in a single host, the application is a process which runs on Linux, but when you move to the cloud, you have containers. When you have to run a lot of these containers in a cloud, the Linux equivalent of it is Kubernetes. So what Linux kernel is to is the Linux ecosystem, Kubernetes is to cloud ecosystem. So it is, we can call Kubernetes as an operating system for the cloud, because it does sort of same things what an operating system does. It doesn't do all of things, but it has been made to basically run those containers. And that's why it became an important driving factor for running your containerized application in the cloud. And at that time, there were a lot of applications, so Mesos is there, Docker Swarm is there, but ultimately Kubernetes won the race, and I'll discuss that why. And before that, so what basically does Kubernetes is, basically it's a declarative API. So if you see, there are two programming paradigms, imperative and declarative. In imperative, you tell how the things should be done and you code those things. But in declarative, you just scan what should be done and leave it to the system. Just like a pilot who's piloting an aeroplane. Imperative means if the pilot is piloting the aeroplane himself and he's looking at all the charts, he's looking at the altitude, he's looking at the direction, and he's constantly changing based on the feedback he's receiving, and he's doing it himself. It's an imperative way of doing things. But if he simply is in autopilot mode, then he just lives in autopilot mode, and the autopilot mode makes sure that whatever altitude has been told, whatever distance, whatever the direction has been told, it just matches that and it does the things on its own. So Kubernetes is a declarative way. So if you see, before imperative, you provide an exact set of instruction to drive the desired state, and system will execute and you will monitor. Basically, your code, you will decide what to do and you will actually code everything in that. But in Kubernetes, the declarative, what is, you define what the state is and the system will make sure that it arrives at that state. So that has actually considerably led to the scaling of this the Kubernetes in terms of ecosystem, as well as all the features which Kubernetes provides with it, is that it's a declarative and not an imperative one. Okay. So now so Kubernetes was the driver, it's a Linux for the cloud, and now you have a cloud native. Now Kubernetes came up from the Google, and Google basically, if you see the genesis of the Kubernetes are from the Borg, which is an sort of container engine in Google, and Borg has again its lineage to work queues and babysitters, so we'll not go into that. But so inside Google, they had one more project going on, which was Omega, and which was again to sort of learnings on the Borg, which has they wanted to actually implement it. But after that, so they formed Google for a team, and they wanted to create something new, and that's why they wanted to sort of put their learnings from Borg and Omega and create something new, and that's how Kubernetes was born inside the Google. And what they did is, Google did is, in 2015, Google actually donated this to Cloud Native Computing Foundation. Now, Cloud Native Foundation is a sister concern of a Linux Foundation, which manages the Linux. And basically, from the Linux Foundation, there was a separate foundation created, which was Cloud Native Computing Foundation. And the first project which was donated to CNCF was Kubernetes. Now, this was donated. Now, if you, people might know Android is an open source. Chromium is an open source. From Google I'm talking about. But they are not fully open source, and you can go and read it. But Google, for Kubernetes, what they did is they donated it, and they wanted it to not be like the Android and the Chromium, and they wanted it to be community managed, and it was donated to CNCF, and then CNCF took Kubernetes as the first project. And what CNCF is an open source software foundation that promotes the adoption of cloud native computing. So that was the sort of about cloud native. So, and what is cloud native? And cloud native computing uses open source software stack to deploy applications as microservices, packaging each part of its container, and orchestrating those containers to optimize resource utilization. So I just bolded it. You have to just say what cloud native means. Use open source software. Make application should be microservices, not monolithic. Microservices, 12-factor app. Go and read about 12-factor app. Third is containerize. Once you are creating microservices, containerize your application. Containerize your application and orchestrate that using any orchestration tool for better visualization. So this is what cloud native computing means. Use open source software to deploy your microservices in a container form through orchestrating engine. And I believe that Cloud Native Foundation has done a tremendous job after 2015 in actually sort of hastening the time to adopt the cloud. And the Kubernetes was the first technology and main driver for it. And there are other technologies sort of where the other projects or other open source projects were further added to it. But Cloud CNCF is the driver. Linux Foundation is the driver for Linux kernel. CNCF is driver for the cloud native landscape. Now, another thing I want to touch is cloud native trail map. So now that you know that by now we realize that Kubernetes is the main orchestration driver sort of cloud operating system, and CNCF is the organization for that. So CNCF also came up with sort of cloud trail map. So it is now that how do we get started with the cloud? Any enterprise, any startup, anyone who wants to get started with the cloud, what are the steps you should follow to become cloud native? And they have precisely to address that I'm showing you the cloud trail map from the CNCF, and this basically is from 1 to 10. It shows all the steps which you should be performing to become cloud native. Now again, this is a tried and tested path which enterprises should apply. This is what CNCF said, and it's not necessary that you have to implement all of the 10 paths. Predominantly, first three points of them are necessary, and then it is up to your requirement based on your application requirement. What are the remaining points you should choose for your cloud native journey? And if you see, sorry for the diagram, it's maybe not that much visible, but I'll encourage you to go to search for cloud trail map CNCF, you'll get that. But the first step when you want to get yourself onboarded to the cloud should be containerization. That should be the first step. And even before that, let's say pre-step should be if you are sort of an enterprise who is actually carrying the legacy code, and it will be a monolith, you should break that monolith into smaller microservices. So microservices, containerize those microservices. So that should be the step 1 in your cloud native journey. So once you have containerized your application using Docker, which is predominantly used, and now we have other options also. Second should be the CI/CD, and again, these are sort of bigger because these are sort of enterprise jargons, but still CI means it's continuous integration and continuous delivery. So you should be continuously basically pushing code and releasing your code, and that release code should get continuously deployed. So I'll encourage you to read more about it if you're not. So second step is, after you have containerized, you should be able to implement CI/CD for your applications. Now, once you have decided the CI/CD and implemented and the technologies which are around CI/CD, the third step is choosing the orchestrator engine. And again, taking from the past which we discussed, is running those containers at scale, the orchestrating those containers. And here, I think it's invariably the de facto winner for the orchestrator engine is Kubernetes. But there are other plates. There's a Docker Swarm is there, Nomad is there, HashiCorp. But yes, you can choose that. But yes, Kubernetes is your orchestration engine of choice. Now, these 3 steps are compulsory for you, your application to get onboarded to the cloud native journey. Now, then the steps after that are whether you want or not, but like fourth, it is important. For example, observability. Now, you have containerized your application and you are running it in a container. You need a way to basically do monitoring of your application and also do the logging of your application. So you have to use certain tools to sort of take into the account the observability and analysis of your application. So that may be the step 4. Step 5 may be the service proxy discovery. So as you have hundreds and thousands of services which are coming onto your cloud, there's a way there's a concept of zero trust networking. How do you trust that these services which are communicating should be trusted among each other? So there you have sort of concept of service meshes coming in, where you implement Istio kind of service mesh network for your application. And again, so service mesh, network policies, distributed database, streaming message, container registry. So all of these based on your requirements, you can choose and make it part of your application, your journey on the cloud native. So I believe you sort of got the basic gist of how to get started with the cloud. So check on cloud roadmap of CNCF and you will get more details. So now you know that what is the path to choose. Now the other thing is what technologies to choose. Now as I told you, CNCF, the first project which was part of it was Kubernetes. Then a lot of these technologies came and projects came to CNCF. So CNCF has 3 stages: sandbox, incubating, and graduate. So the project which joins the CNCF Foundation is first a sandbox, and the last stage is graduate. graduated projects are those projects wherein CNCF actually sort of gives it's way of saying that these applications, these products, open source products, or whatever they are ready for enterprise consumptions. And Kubernetes was first graduate project. Then second was Prometheus, which is a monitoring solution. Now we have NY, Jaeger, we have Vitesse, and there are a lot of around 9 to 10 products which are graduate, which an enterprise can use in their cloud native journey. And this is a cloud landscape. Again, I recommend you search on the Google landscape.cncf.io, and you will get this page. And this page talks about all of the technologies in the cloud space which are available for you to use and which come under CNCF umbrella. And this is such a humongous task just to look at it. Forget about knowing about all these technologies, but it just tells you about how many projects are currently running under CNCF, and that's why the CNCF is a big driver, because it is encouraging all those open source products to work cohesively in a cloud native, cloud agnostic way, such that enterprise who only chooses the CNCF product doesn't get vendor locked in that case. Okay. Now you know the cloud native journey, you know the cloud landscape, what technologies are, and I just give an example. Like I have to build an application. What I've done is, you see, I have to choose various different. I have chosen various products or projects from this cloud landscape to build my project, and I just marked them in red. And these are some of the projects which I choose. And again, it's a big task. Just wanted to elaborate whatever I've shown it here. I just am now sort of zooming it. Now, first is provisioning. So for the cloud native journey, and I'm getting on board with the cloud, I have to provision the infrastructure first. And what are the tools I need to provision? And again, all of them I have taken over from this, the CNCF earlier. So, and this is what tools I have used. This is for my application. Again, I need Terraform. Again, Terraform is infrastructure as a code. It's used to sort of create infrastructure in cloud through configuration files. So, and moreover, Terraform is cloud agnostic. Whenever you create code using Terraform, it can run on any cloud. It can run your on-premise infrastructure, and it's cloud. So I chose Terraform for my cloud infrastructure automation. You need a place for your registry to store your containers. And that's where I have used Quay registry. It will be a place for me to store the containers quickly. Security. I also need to think about the security in terms of the containers which I have created, and there may be binaries, open source binaries I have used, and I need to sort of keep on scanning those open source binaries for any vulnerabilities, and I use a security tool for that. In this case, I use Black Duck. Then this is key management. Key management, SSH keys. So I need to manage my SSH keys, and I use an open source Vault solution for the key management. Again, I'm just quickly browsing. Now provisioning is done, infrastructure related things are taken care, and all of these are again CNCF projects. Now coming to the runtime. Runtime, you have storage, network, and container runtime. Storage, I have chosen Minio. I am using object storage. I use Minio for that. It's an S3 compatible object storage for me, works fine. Container runtime, I have chosen Docker Container D, and Container D is sort of an open source version of Docker, which they gave it to CNCF. And container runtime is when you are running. It's basically a Docker engine. Some people are saying it's the runtime engine which will help running your images. Network, I chosen Flannel. I need to hurry. Orchestrator management, I have chosen Kubernetes. Proxy. If I want, I'm running my application and I need AWS. People from outside should be able to connect to my application inside. So for that, I am using Nginx as an ingress a proxy. Service mesh. I'm running a lot of applications, and I need those applications to authenticate to each other, do mutual TLS, and I don't want myself to be managing those certificates. And one of the functionality which Istio is providing me is a mutual TLS. So I'm using Istio Service Mesh for that. And app development. You have database. You need to have I need to have for my application database. I'm using a Vitess database, which is a sort of MySQL cluster database, and it's scalable. It helps scale MySQL horizontally. This is Vitess. Helm. If I want to deploy my applications on the cloud, Helm is an equivalent of Yum. Messaging. I'm using Kafka. CI/CD. If I have to do that, is CI/CD, as I mentioned, is continuous integration continuous. I'm using Jenkins, and to top of it, I need to do monitoring and logging, and I'm using Prometheus, Grafana, Fluentd, Elasticsearch, Kibana, Elasticsearch. So the point I want to drive here is it's an application. I want to go cloud native, and this is the gamut of the projects or the open source things I have to work with. Now I need to have expertise of the R. And it's very. If I am say the new organization which is born in cloud, yeah, I'm operating in a gray field. I can work on it. I can do these things. But if I'm an enterprise, it's very difficult for me to just use those open source. But the point I wanted to bring is, cloud is complex. It's a simple application which I want to deploy. I needed all those. Forget about things when the applications are complex. You will need quite a lot of things in the orchestrator. I have not talked about gRPCs. I have not talked about APIs. I have not talked about all the things. This is a simple application, and you should see, to become a cloud native, how complex it becomes. So if you are willing to take, if you are a new company, if you are a Netflix, if you are a Facebook, you are just coming up with the cloud, yes, you can go out. But for an enterprise who's for long in the cloud space is already there and has legacy code also, it's so difficult for him to actually use all those technologies. And this is where I believe OpenShift gives the meaning. So whatever I had shown in this slide, it's a quite complex thing, a lot of different technologies, and you have to work with, like there are around 12 to 15 technologies separately. The OpenShift will give you a combined package of it. It's a single shop sort of solution for all of your queries. So if you see, it's Kubernetes, it is clustering, monitoring, showback, registry, logging, middleware functions, dev tools, CI/CD, service mesh, Kubernetes. So it is a package. So just to give an analogy quickly, Red Hat operating system, RHEL, is basically taking Linux kernel and building tooling on top of it and selling it as a Red Hat enterprise, and we pay for the service. So same thing OpenShift did is, it took Kubernetes, which is the, let's say, kernel of the cloud operating system. It took Kubernetes, it took, earlier it was Docker, now it is Cryo, and it packaged it, and it has this Red Hat Enterprise Core OS, and it packaged it and it built tooling on top of it, and it gave you a PaaS solution. So now if you are an enterprise and you are going into cloud, you don't have to actually sort of go into the cloud native. You don't have to go into the service. You can use OpenShift and you can get all of these things here. And if there are third-party tools, for example, we have this Vitess database, other things. So MySQL, MongoDB. For them also, you will have Kubernetes has OpenShift has operators in 4.x, where it will allow you to deploy all those applications. So quickly, it's OpenShift is to sort of demystify the complexities of the cloud and make it easy for enterprises or anyone to consume those resources of the cloud and make it cloud native. I think I'm already, I have only 5 minutes. I want to take if there are any questions or if you want me to proceed. So Ganesh.
Thank you, Himanshu. Are you done with the presentation? All your slides you went through, or?
I wanted to cover one more. This I want to discuss about the architecture of the OpenShift. But
Yeah, go ahead. Please go ahead.
okay.
We love to hear from you, about that OpenShift, and you complete your, the 18
Okay.
slides. Yep. Go ahead, please.
Yeah. So this is an important thing to remember here is OpenShift is a multi-cloud operating system. So this is the problem which enterprises face is if they go to Google, they will get struggles to GCP. If they are Azure, then so there is no way, like if I'm running on AWS, like I cannot go and directly go into Azure, or I cannot go into GCP and all those things. So the issue here is there is a lack of multi-cloud operating system wherein sort of you could sort of deploy your application on that, and then that operating system you could sort of move around on different clouds. I think OpenShift actually fills that space perfectly well. And if you see in the down of the slide, it can run on physical hardware, it can run on virtual hardware, it can run in private cloud, and it can run on public cloud. So means once you are in a position to run your application on OpenShift, then it doesn't matter. The underlying cloud doesn't matter. You can run your application on an in-premise private cloud. You can run your applications on AWS. You can run your application on Azure or GCP. So basically, you have become now cloud agnostic. So that is the beauty of OpenShift. It's a multi-cloud operating system, so as to call. So that's one point I wanted to bring. And lastly, quickly, I wanted to show you the architecture of OpenShift is it has basically, like I'm showing here, so don't go into the boxes what API controller, I don't want to make it complex now. It's basically you have three masters, like at least three masters. It's just to avoid split brain personality or syndrome, or to maintain the quorum. So you will have the odd number of masters, and you have pods. And what the masters are, the master is the host, or these are the hosts that contain master components, and these are these components, API controller server and other things. And basically the job on a high level is to basically get the workload and get that workload deployed on the worker nodes. And on a high level, that is what it is. And if you see, various actors in an OpenShift are infrastructure people, development people, and end users. Or I mentioned them as application 1 and application 2 users. So these are the type of people who will contain. Either you will connect to maintain the infrastructure, or to create some development stuff in that, or you want to access the services which are running on OpenShift. Okay, and quickly, and how do you connect to OpenShift infrastructure is you don't connect directly to OpenShift. So basically, you can connect to an enterprise DNS. So when I say DNS, so OpenShift actually exposes itself to the outside world is through a vanity URL. It may be like www.openpower.openshift.com, and that's a vanity URL which is exposed to all the people, all the actors which are going to work or use this OpenShift environment. They are going to use, and they are going to connect to enterprise DNS. So that is your entry to the OpenShift environment. And once you hit the DNS, second is that gets routed to the load balancer. And why load balancer? Because the load needs to be so. In case of one master dies, the load balancer is not enough to redirect it to the one of the available master which is there. So that load balancing, both at the master level and also worker level, that load balancing is done by an enterprise load balancer. And in like for example, enterprise DNS will be if you are it can be TCP wave or in your case, or it can and the load balancer can be anything. F5 load balancers or NSX load balancers which you can use, and once the load balancer hits, and then the connections can go to the masters, and then it can hit to the pod, and that's how. So for example, application, if I am an end user and I am actually utilizing a service which is web service which is running inside a pod, I will actually hit an enterprise DNS URL, myservice.com, myservice.openpower.com, and that will get routed to load balancer. Load balancer will then actually get it routed to a particular, what in OpenShift is a concept of route, which is an ingress to the OpenShift environment, and then route will actually, which is an HA proxy server, like in the earlier Nginx, but in OpenShift there's a HA proxy server sitting, and then HA proxy server will redirect that app1 to an app1 application, and where its pod is running, and it will actually get its work done. So I think, yeah, it's already 1 hour, so I'll stop here. And so I had tried to just make it so that we could finish it in 1 hour.
Thank you, Himanshu, for your wonderful insights on, OpenShift, Kubernetes, and, your enterprise, the jargons. I'm really amazed. There are a lot of new jargons, I heard from you today. Thank you very much. And there is a question, asked by Professor and Dr. Gopal from Anna University. His question is, what is the minimum needed footprint on the host machine to connect to the cloud in the deployment models cited in your lecture?
Okay. If I think if it is I should say that the infrastructure which I have here, so it's a bit complex because I have given an example of a generic enterprise application. So I should say it, for example, OpenShift itself requires you at least 4 cores, even if you are trying to deploy the OKD. But like to deploy this sort of infrastructure, because the good thing about it is because you are using Kubernetes and you are actually, it's not that you need a physical core. You can divide a physical core into 1,000 cores, 1,000 millicore, and you can assign those things. So ideally, I should see the infrastructure which I have shown, it should be like, I am sure that it should be done in a matter of, let's say, 8 cores and 32 gig of RAM. Now, this is the deploying part of it. The actual workload running, then things might change. So, 8 core 32 gig RAM should be sufficient for this infrastructure. But when it comes to when you run your workload and then what your workload requires, that actually is now a different bulk altogether. But because it allows you to chop, and you can give even 100 millicores, and you can sort of that way, so you can sort of adjust your requirements. So I should say the kind of infrastructure which I have shown, 8 core 32 gigs of RAM, but I have run an OpenShift, the open source version, which is freely available on even 2 core machine also on a virtual box. Just for demo purpose, I can show that. But 8 core 32 gig RAM should be sufficient for this side of infrastructure.
Yeah, thank you, Himanshu. I think your answer, your question, you answered, the professor's question. And
Ganesan, can I ask one question?
Yeah, please go ahead. Please go ahead, Professor Agya.
Sure.
Yep.
Hi, Dr. Dhar, for your wonderful presentation and wonderful work on this containerization and virtualization. So I actually started getting my hands dirty on these containerization and virtualization things. So I am not sure whether this question is really related to what you have presented or not, but it is mostly on my research. So, do you have any infrastructure? Did you prepare any infrastructure for this, let's say for this Hadoop ecosystem, containerizing, let's say Docker containers are spawning up in the same machines and creating a Hadoop cluster, and then everyone can start working on it. Do you have that type of infrastructure? Did you get a chance to work on that anytime?
So I have not, so Hadoop I used, I'm talking about 2015 when I used Hadoop. And so strictly I am not using Hadoop after that because I think Hadoop has now a replacement, and now you have more of streaming than sort of a batch processing. So world has moved forward from batch processing to sort of live streaming, where you have Apache, Flume is there, Spark is there. So Hadoop I have not now touched for quite a while. So that's why I didn't containerize another thing. And the latest ones are like nowadays. I'm talking about like what is the hype now. Hadoop is not being used, so that's why you will not see much of the efforts going there. And if you see the CNCF page which I showed, the most of the sort of data, the products which are doing with the are basically streaming products. So yes, so unfortunately I have not worked on the Hadoop, and it's mostly, if I have worked on, it is on the in-memory streaming project like Apache Flume and all those.
Okay, so I mean, yeah, I mean, since I'm working on that type of project, so possibly we can discuss a little bit offline. So would you be interested to collaborate with some part of my research work, which is related to this Hadoop stack on this Docker containerization and everything? So
yeah, Himanshu, Professor Agya is from University of Wisconsin, and I initially announced him as a panelist actually, and he is also like a real collaborator for our OpenPOWER and the open hardware ecosystem.
Okay. Yeah, we can talk offline on this.
Sure.
Okay, I'll be happy to talk.
Yeah.
Thank you.
Yeah, very good, Professor Agya. Thanks for asking this wonderful question, and thanks to Himanshu. I think if you have let's move on to the second presentation. Before that, Himanshu, thanks again for your wonderful insights on OpenShift, Kubernetes, and the hybrid cloud. Thank you, and you can continue to stay here. There is a talk from IBM experts on OpenShift and the hybrid cloud. Thanks, Himanshu. And audience and panelists, let's move on to the next presentation. I'd like to invite my colleague Krishna as well as Mithun to share their experiences on the hybrid cloud OpenShift. Krishna and Mithun, please go ahead.
Himanshu, thank you for your informative session. If you could...
Krishna, can you go big? Can you increase your volume or something?
Sure.
It's not audible.
Sure, Ganesh. I think Mithun is going to present us in this talk, and I'm going to give you a brief demo at the end of the talk.
Sure, it's audible.
Yeah, sure. Yeah, thank you, Ganesh. Is my voice audible now?
Yeah, it's audible. Please go ahead.
Yeah. Thank you, Himanshu, for your informative session. First, I would like to thank, because that sets up very nicely for our presentation, which we will discuss in 30 minutes or so. And I would like to thank Ganeshan as well for allowing us to present this, for the opportunity for presenting this. Good morning and good evening, everyone. Thanks for all your time for attending this session. So let me introduce myself. I'm Mithun. I'm with my colleague Krishna. We both work as software engineers in IBM India ISV team, where we enable clients to port their application onto Linux on Power ecosystem. We will discuss more in this presentation on Linux on Power, IBM Power architecture as a whole, and also we are involved in creating benchmarks and running performance suits and coming up with benchmarks with competitive products in the market. So to start with, looking at the heading, so it's just text and slang to say that you are containerizing your application and you are packing everything up into a single container and you are deploying it on OpenShift, which is called as Pack'em and Stack'em, which we have mentioned. And also we will go through the advantages of running OpenShift on IBM Power Platform as a whole. We will share our benchmark study, which we have done in the subsequent slides, right? So I would like to make clear on the agenda, which we are going to discuss in next 30 minutes or so. First, I would like to emphasize on IBM and Red Hat partnership, how IBM and Red Hat together have come up with the products which are very relevant for the industry. And then we will go through the Red Hat OpenShift overview as a product. And then we will go through the use cases where exactly the OpenShift can be used. And we will also see what are the different hardware available in order to better execute the workloads along with the OpenShift product as a whole. And then we will jump into the performance study, which is a benchmark which we have done. We will see the objective, why we have done the benchmark, so that it could be consumed both by academia as well as the industry. We will also discuss in brief, we will spend some time on the workload which we have used, why we have used the workload, and how we have designed it, and how we have come up with the numbers with a competitive product in the market, right? At the end, whatever we will go through at the start, we will go through a demo, which with a brief demo, which will give you a hands-on kind of an experience where my colleague Harsha will go through the demo of deploying this in the OpenShift cluster, right? So coming to the Red Hat, IBM and Red Hat partnership. So it is nothing to do with the acquisition, but before IBM, Red Hat becoming part of IBM, and Red Hat have worked together. So Red Hat has, like we saw in the previous session, so it has a list of its products. It has a lot of products for the industry, and IBM Power Systems IBM Power Systems as a main has worked with Red Hat in order to bring all the latest and greatest software into the industry. So you might know about, everyone knows about RHEL, right? RHEL. So that is the industry accepted distribution and most widely used Linux operating system. And you can see like OpenShift, Kubernetes, and OpenStack. We saw OpenShift in the previous session, and Kubernetes, which is a container orchestration platform, and also infrastructure as a service from OpenStack, right? So all these products are optimized to run on IBM Power Systems. So we will see in the next slide how it is tailor-made, how the Red Hat products are tailor-made to run on IBM Power Systems, right? So coming to the Red Hat OpenShift itself, we have, it is a container orchestration mechanism. So it has its own registry, it has its own list of software which come in the Red Hat OpenShift registry inbuilt. IBM and Red Hat have worked together to get all these products and suits to be in the IBM, in the Red Hat OpenShift registry itself, right? So, so it is built on Kubernetes. Again, it is open source, like we saw in the previous session also. Coming to the use cases of Red Hat OpenShift, right? So there are a lot of use cases, but we have identified mainly three verticals where we can say the Red Hat OpenShift has the utility. So first thing is application and infrastructure modernization. Like you have a legacy application. Everyone would have been well versed with the application. Legacy application, right? So you have a front end and you have a back end database running. Suppose if you want to modernize it and if you want to bring it to cloud. So what are the utilities of uses of bringing it to the cloud? Suppose if you have you might have heard the word DevOps. So you might have a lot of developers in your organization. You might have testers. So everyone wants to get hold of the application. So in order to cater to these kind of need, you might containerize the application in a microservices kind of an architecture, and you can provision it, right? So that is one of the advantages of containerizing and giving it to multiple consumers, right, within your organization. And also, while you are doing it, while you are containerizing the application, you can say that you are having your application in production. Suppose if you want to upgrade some part of your software, so you don't have to really shut down all the containers. You can patch part of the infrastructure, and your application might well be running with the other utilities, and you can upgrade certain part of the software and then you can move ahead, right? And also OpenShift provides in its internal registry a lot of pre-built softwares in the catalog. You can just go and provision those softwares in order for your application to run, right? So when you want to modernize the application, OpenShift provides all the utilities which are needed. And coming to the next vertical, which is the data-centric cloud applications, right? So when we say data-centric applications, previously we used to have a public cloud where you had all the data and you would take all your data to the compute. Nowadays, there is a lot of data. Everywhere the data is being generated. So moving the data from your local environment into the public cloud might be a costly affair, right? So you might have to bring compute to your data. So that's where OpenShift plays a part. You can have your on-prem cloud kind of an environment where you are getting all your compute to the data, right? So that is where OpenShift plays a best part there. And coming to the third vertical, artificial intelligence and machine learning, IBM with Red Hat has been working on this. We have a tailor-made software called as AC922. We have collaboration with NVIDIA, and we have GPU inbuilt into our servers, and those servers are tailor-made to run artificial and machine learning kind of workloads. And we have NVLink, which is an industry standard, which will help you move the data between your GPU and CPU faster, right? So those are some of the use cases which we can broadly classify, right? So here, I would like to briefly emphasize on what IBM Power family, what are the different servers we have. So we have LC922 kind of a server, which is tailor-made for big data analytics, right? So we have something called as PCIe Gen 4 kind of a network link, which will help you to move data faster into your CPU and process faster. So each of the server, like AC922 is built for AI workloads. It has NVIDIA GPUs, which will come in built with NVLink. So you can run your, you can train your model faster, right? An AI model faster. And then we can see at the right hand side of the slide, we have enterprise grade servers, which are basically primarily made for relational databases and enterprise kind of an architecture, where scale out kind of an architecture, where you are growing and you want to increase your infrastructure, you can go with enterprise grade of servers. And in the middle, you can see the S-class servers, S and H class servers. So those have higher memory footprint. Suppose SAP HANA, right? SAP HANA and MongoDB. So most of the processing happens in the memory. So you need to have a big memory in order to cater to the requirement, right? So these kind of servers have a lot of memory footprint, and that's the reason those are tailor-made for SAP HANA and MongoDB kind of workload. Right? So that is the Power 9 family. Right? And mainly I want to emphasize on how IBM's power systems are built for data intensive workload. So you need to have a workload which is CPU intensive as well as data intensive at the same time. So like we saw in the previous slide, the servers are tailor-made such that they have high memory footprint, and you can move a lot of your data into the CPU, into the memory, and you can process it. So we have identified a workload which is data intensive, at the same time it is CPU intensive in the benchmark study, which we are going to discuss. Right. So now we will be jumping into the benchmark which we have done. So to start with, we will see what is the objective. We have ran the workload, we have developed the benchmark, and we have ran it on IBM L922 kind of a server, and we are comparing with competitive x86 architecture, which is an Skylake machine, right? So first thing was to identify the workload. We have taken workload from MongoDB, which is available in their MongoDB website, which they gave it out, right? So we have taken something which is there publicly available. We have taken that MongoDB workload, which is a geospatial workload, and it has application which is built using Node.js, which is a mean stack, that is MongoDB, Express.js, AngularJS, and Node, right? So in this particular workload, it mainly makes use of MongoDB and Node.js. And we have defined SLS such that the transaction end to end, so we are generating the workload from a JMeter box, and it is going through this OCP cluster, and the request goes to the OCP cluster and it comes back. So each transaction should be completing in 999 milliseconds. If it is not completing within 999 milliseconds, we have not considered that transaction as valid in the benchmark, right? And at the end, we have also catered to the container density. We have seen how many containers we can pack in a server from IBM Power Systems compared to x86. The reason we have to be aware of the container density, because in a DevOps kind of a scenario like we discussed, right? So you can provision as many containers as possible when you can have multiple containers, right? And when you have multiple containers running in a single machine, so your price performance per core, in one core you can run multiple containers, thereby your price also decreases per core, per container, right? So that is the price performance advantage you get while running on IBM Power Systems, right? So that is something which we are going to see now. Yeah. So coming to the workload itself, so this is a very busy slide, so I'll make it as simple as possible. Suppose if you have every day in and day out, we will take out our mobile and we will try to search something in Google Map, right? So imagine something like you are trying to find a nearby restaurant which is having a very good review. So you will open your Google Map and then you will type for a restaurants nearby, right? So when you do that, the workload does the similar thing. So it will pick up the neighborhood. So when we are searching for a restaurant, it is not enough to get the restaurant itself. It would also go and see what are the neighborhoods which are there in the particular location, and it would get that information as well, right? So the workload is simulating the same thing. When a user tries to search for a restaurant, it will go and it will get all the neighborhood information. It will get all the restaurants in the neighborhood, right? So if you see this, there are 5 APIs which in turn spawns up when you are sending a single request, right? So suppose considering there are 4 users and you are searching for a restaurant 10 times, internally it will be like 4 into 10 into 5, right? So around 200 transaction would be happening there, right? So we have JMeter box which has been simulating this workload, and when we are running the workload for 8 minutes, it has generated these many transactions, right? Like we see. So based on that, we have scaled up the workload, right? And you can see there is some data which is also involved when we are searching for that particular restaurant. Some request goes and some data comes back as well, right? So coming to the software stack which we have used, so we have used Power VM, which is a standard hypervisor in order to create virtual machines on IBM Power 9 enterprise grade of servers, right? On x86 we have used KVM, which is a de facto standard for virtualization on x86 on Intel. While we did the benchmark, 3.11 was the latest version. But now we are in the process of coming up with the benchmark on 4.3 as well. And operating system by then was 7.6, RHEL 7.6, but we have latest and greatest now 8.2 as well. But the reason for showing this particular software stack is the software which we are running on IBM Power Systems compared to Intel architecture is similar across all the stack, right? If we see the MongoDB version, it is same. If you see the Node.js version, it is same from Power to x86. So this is very important while we come up with a benchmark. So it should be similar, right, in order to If there are some outliers, it will help us get all those things out of the benchmark. Right? So this is the architecture which we have used. So I would so left hand side, if we see our left hand side, we have IBM Power System cluster. On the right hand side, we have Intel cluster. OpenShift doesn't as of now, it doesn't support having multiple different architectures in a single cluster, but we have tested that it works fine, but it is up to Red Hat to come out with such kind of support, right? But for the sanctity of benchmark, we have created two clusters. One is separate for IBM Power Systems and another one is separate for Intel. So if we see the configuration, we have used the load generator, which is a JMeter box, which is simulating your searching of the restaurant. So it is being simulated from the JMeter box. This is similar to both the clusters in order to generate the same workload, right? So this is similar for both the clusters. If you see the host, we have the system under test running under IBM Power System L922 class of servers, which has around 20 cores. Similarly on Intel, it has more number of cores, 36 cores. And we are using, like we discussed, we saw in the previous section, we have used Power VM as a virtualization software. And LPAR is the notion, it is a standard notion which we call for, which we designate a VM in Power VM virtualization aspect, right? On Intel, we have 2 VMs. So these are the systems under test. We'll see the data flow. Right. So when we are generating the load, we have created something called as root in OCP console, right? So that is nothing but an ingress controller. It will, each IBM cluster will have a separate route in order to route all the requests, and there will be a different route in order to route the request to the x86, right? So when a requests are made based on the OCP route, it gets routed to IBM hardware, and then it gets routed to x86 accordingly, right? And also, if you see here, we have bundled both MongoDB and Node.js application into a single container, and it has been running as a separate instance altogether on different containers, right? So at the end of the workload, when we have concluded this exercise, we can see that on IBM Power L92 server with 20 core and 256 GB of RAM and 2 LPARs, 2 logical entities, virtual machines, which we have created, we were able to run around 174 containers, whereas on Intel, even though it has 36 cores on Intel Xeon SP-based server, we are able to run only 98 containers, right? And also, we can see that there is significant improvement in the transactions per second, which we have got compared to x86 server. So you can run more number of containers per core, right? So if you divide the number of containers per core, you will get around 8 to 9 containers, which you can run on IBM Power Systems, whereas on Intel, you can run around 2 to 3 containers. So what does it translate to? So for each core, you will be spending very less, right, on IBM Power Systems compared to Intel Xeon SB-based server, which we have used in the benchmark. Right. This has already been emphasized in the last session, but yeah, so it is just an abstract of your operating system, which will have all the components for your application to run, right? It is very light version of your operating system, I can say, with all the components for your application to run, right? And pod is a logical entity, which we call. So you can while you are deploying these pods, you can designate all this. You can give a different label to different pods. You can specify how much hardware resources it has to use, like CPU, memory, and storage. So all those things you can specify while deploying. In the demo, we will go through all this, how it has been designated and how we are deploying, right? And I'll not spend more time here. Similar to what we did with MongoDB and Node.js, some of our teams have tested the industry most widely used open source AI frameworks, Caffe, TensorFlow, right? On an AC 922 class of servers, which are tailored made for artificial intelligence kind of a workload. So we have a large model support. Suppose if you have a very big image processing which needs to be done, you can load all the image into the memory. So there is a large model support. There is distributed deep learning. You have different nodes working together. There will be, the learning will be faster. There will be coherence in order to share the data, right? And there will be, and we have support for the industry standard NVLink as well in order to move the data between CPU and GPU faster. Right? So summarizing what we have gone through in terms of benchmark, right? So for MongoDB kind of a workload, you will get around 3x greater container per core comparing with Intel, right? And also you will get around 2x, 2.6x better performance, price performance advantage. And with AI models, they have run the workload which was taking 3.1 hours on an Intel Xeon based servers. It will complete within 48 minutes. It has completed within 48 minutes on a power based system, right? And you can see all the power architecture has been, IBM has been part of OpenPOWER consortium, and all the hardware has been, is open for to see and develop something on top of the architecture. And there is a support for OpenCAPI kind of a link also, right? Something needs to be, something which has been in development for the links in order to see how the data could be transferred, right? So that is also there. So all in all, you will get a lot of advantage by using IBM Power Systems compared to Intel based x86 based servers, right? So in summary, again, I want to emphasize, you will be able to run more containers. Per container, you will be getting more performance, and per container, you will be spending very less, right? So all in all, there will be advantage in terms of greater number of containers as well as greater throughput, and you will be paying less compared to the competitive product, right? Probably with that, I will hand over to my colleague Harsha for the demo. We can take the, so once you see the demo, you will be able to visualize, and then we can take the questions. Right?
Sure, Mithun. I think it was a very wonderful context in terms of understanding why one should run OpenShift on Power and what are the advantages associated by just merely shifting towards the Power architecture. So what I'm going to take you guys through right now in this particular demo is, just give me a quick moment. I'm going to share my screen. Okay, Mithun, can you kindly bring up the demo? For some reason, it's not allowing me to show.
Sure, just give me a second.
Okay. Okay, can you see my screen, Ganesh and Mithun?
Yeah, sure.
Yes, Krishna, sure. Yes.
Okay, so it was a last minute hiccup, but I'm glad it came through. So what I'm going to show you in this next 5 to couple minutes in this particular demo video is how we are going to use the same experiences and tools with which we deploy your application on OpenShift Container Platform, and how we are going to deploy it on OCP 4.3 environment on IBM Power Systems. So, and then all the advantages and then everything that comes has already been discussed. This is just that do not think of IBM Power Systems as a foreign architecture. It is as simple as deploying your application on Intel systems. It's as similar as that, right? So what we are seeing right now on the screen is OpenShift Container Platform's web console, which is accessed to your web browser. I'm going to log in as a standard user, and the application which Mithun has discussed is a 2-tier application. which is made up of MongoDB and Node.js. So what we have done together is we have put together all of the pieces in terms of deployment files, which is readily available in this GitHub URL that you're seeing on the screen. And then we're going to deploy it on a project space. You can think of project space as a workspace environment, an isolated workspace environment, where you can deploy your application and play through it. I'm going to toggle between the administrator and developer mode, where switching to developer mode gives me access to the dashboard utilities via which I can deploy my pre-compiled application directly onto the system. So I have selected the tile YAML files, where I can consume a pre-existing YAML files, where these YAML files are nothing but representation of my application logic. And to represent your application logic, you usually make use of service YAML files and deployment configuration files. Since this is a two-tier application, I have 4 YAML files, which corresponds to both MongoDB and Node services files, Node.js services files, right? And then once the application gets deployed, right? Just gonna skip through this particular moment because this is the same YAML files that gets to be deployed multiple times, right? Right. So once this particular YAML file gets deployed and my application is up and running, I would want to see the status of my application. Is it healthy or not? You can see right now on the screen, it is trying to create the container. So what's happening in the backend is it is trying to pull the relevant Docker image based on your architecture, and it is trying to spin up. The application logic, which is already embedded into my YAML files, helps stitch up the Node.js container to MongoDB container. And post that, they are able to communicate with each other, and I can access that particular application outside the cluster. Right, so this is again a validation step. Basically, this will help tell me whether my MongoDB services are up and running or not. Right, so yeah, it seems there's a lot of activity that is going on. And right now we can see, right here we can see that I'm accessing the terminal of MongoDB container, where which I have the MongoDB services up and running. So this is a logical validation step. Basically, we may or may not have to do this particularly. And then I'm going to switch to administrator mode. In order to access this particular application outside OpenShift cluster, what I'm going to do is I'm going to create a route, which basically Nitin has mentioned in his previous demo, in his previous chats, right? So this particular route helps me expose my application logic outside OpenShift cluster. I'm going to map this particular route to leverage Node.js endpoints, with which the moment I hit on this particular URL, right? So it kind of tells me, hey, this is where my logic is residing, and this is where you could access these endpoint URLs. In order to leverage the data inside the MongoDB container, what we have done is we have created endpoint API definitions, which is pre-baked inside the container logic. The moment I hit that particular URL, it translates to a MongoDB equivalent query, and it fetches the data out. So this is what we are seeing right now. So I'm just going to highlight on that particular piece of information, which kind of tells me that I wanted to see the inspection carried out in my vicinity between this particular pin codes. And it told me that, hey, there are 747 inspections which are currently happening in this particular vicinity of your choice. So if I have to log into the MongoDB container and see, hey, is the data actually valid? So what I'm going to do again over here is switch to developer mode and then access the MongoDB container, and then perform at the backend equivalent commands where I'm trying to query nearest restaurant available in my vicinity. So yeah, so I just connected to my proof point database in which I try set up the query logic, and I perform what you can see over here is find the nearest restaurant in my vicinity, and it gives me street of foods is the nearest one which is available in the vicinity at this point. So that's the whole demo that I wanted to talk to and take you through. So I'll just stop sharing my screen and take up any questions.
Thank you, Arsha, as well as Mithun for the the deep dive on OpenShift and the demo too. And audience panelists, do you have any questions for Arsha and Mithun?
So, hey Ganesan, I have one question for both Harsha and Mithun.
Yeah, please go ahead.
Regarding these OpenShift related things. So yeah, I mean, so your presentation and demo was really great. So I was wondering, do you have any, what should I say? Do you have any comparison between this Docker and this OpenShift? Is there any performance related issues that you have observed, or so one aspect is performance, if there is any performance related difference, and if there is any like in terms of convenience of working or something. So can you shed some light on that? I mean, yeah, I mean, which one is easy to work? What are the actual benefits when comparing Docker and OpenShift, something like that?
Yeah, so Mithun, I would want to answer that particular question. Docker and OpenShift go hand in hand, right? So it is not actually a fair comparison to give it. This is not an apple-to-apple comparison in a way. The reason I say is the images that we saw just now, which were running on OpenShift Container Platform, were actually the Docker images. So the benefit of leveraging OpenShift Container Platform is the scalability aspect of it. You do not have to worry where your container images are running. Even if you have multiple hosts in which, for example, we had 2 compute or 2 worker nodes in this particular cluster exercise that we saw. Even if one of the server goes down or if it gets out of resources, OpenShift has the intelligence and capability to schedule it on the other systems. But whereas if you take out the notion of OpenShift Container Platform altogether, scheduling your Docker across, scheduling only your Docker across systems, the scalability aspect comes into the picture and it hits pretty badly. So to make the life easier, that's where the OpenShift Container Platform comes into the picture and stitches together your entire farm of clusters. We don't have to worry where it's going to get scheduled and where it's going to is this working, in fact. So, OpenShift and Docker they actually have to coexist with each other in a way. So you cannot compare which one is better in a way. If you ask me, I would rather say OpenShift Container Platform because of the scalability benefits it brings onto the table.
This is Himanshu. Just to add what Krishna said, giving an industry perspective, Docker is one of the components in OpenShift. Docker is a sort of a build deploy tool, but OpenShift is a PaaS platform. So OpenShift, along with a lot of other technologies, uses Docker as a part of build container. And OpenShift has been using Docker till now, but recent changes have gone into OpenShift, where if you see in OpenShift 4.x, Docker is not using, OpenShift is not using Docker for the runtime, but instead is using Cryo for the runtime. So going forward, the dependencies on Docker will get more reduced. Runtime has changed. And Docker getting replaced with the Cryo in 4.x, and even the runtime, after the runtime, this is the image registry will also get changed. So the dependency on Docker is getting less and less for OpenShift, and OpenShift is moving towards more open containerization, which is an OCI. Open Container Initiative, and it's using all the Docker related technologies which are Open Container Initiative, those certifies. Cryo being one of them, Podman being another them. So in the industry, there is a trend wherein people are sort of moving ahead from Docker towards, let's say, Podman, and you can check the differences there. But yes, the shift is happening wherein OpenShift is moving away from the usage of Docker as one of its components.
Mm-hmm. Okay,
Thank you
great.
all.
Sure.
Yeah, Professor,
Yes.
continue. Just continue. Yep.
That's,
Okay, yeah, sure. Thanks for the nice explanations. So, I mean, I just started working on this virtualization and everything. So, pardon my ignorance if I am just asking very basic question. So, I mean, so in Docker, when I have worked earlier, so I used like Kubernetes platform for to spawn lots of different Docker containers and everything. So this OpenShift is right nowadays. OpenShift is taking the responsibility of that part. What you are saying, or I'm getting it completely wrong?
Yes. So basically, as I told, I'm just giving you an analogy. If you see Red Hat Enterprise Limited, Red Hat Enterprise Limited as an open source component inside is a Linux kernel, and it builds on top of it various tooling and other OS features it provides, and that makes it a complete operating system. So kernel plus other this functionality make it a Red Hat operating system. Same analogy you can take it to OpenShift. OpenShift takes Kubernetes as its kernel sort of core component. It takes Cryo, earlier it was Docker for building. It takes Cryo as its core component. Then these two components plus it has a base Red Hat core operating system, and it builds a lot of tooling on top of it. So yes, Kubernetes is its kernel, Docker is its Docker Cryo is its building tool, but and tooling on top of it is source image is there. You have operator support and all those things. So they make it a big solution which is offered to the enterprises as an OpenShift environment. So Kubernetes is a sort of a hard kernel of this entire OpenShift ecosystem.
Okay,
Just to
I got
add
it.
what,
Thanks for the nice explanation.
yeah, so just to add to what Himanshu mentioned, right? So OpenShift Container Platform has a pretty good ecosystem presence around it, which allows you to just leverage those application installations directly onto the cluster. There is a considerable amount of effort that one has to place in order to integrate those open ecosystem components onto Kubernetes environment. So if you just if you want to focus on application development quickly and in the realization time of performing your application development quickly, you could rather leverage OpenShift Container Platform directly and then focus on your application enhancements and beautifications rather. So that's what OpenShift Container Platform brings onto the table in a way.
I see. Thanks. Thanks for the wonderful answer. Thanks.
This is Gopal here. I have been thinking in this manner. Whatever is the virtual machine or virtualizer, it should have some component of application programming interface, application binary interface, and a hardware abstraction layer. The combination is likely to tell me what is the number of cores. The footprint is obvious, 2.7, 8 point plus something. But it does not guarantee that the cores are evenly loaded or there is some load balancing happening on the cores. Your comment.
Okay, so to answer your question, in the even loaded is all of your containers evenly loaded, and then can you assign a piece of resources only to your container for its own utilization? To answer it straightforwardly, yes. You could. You have the capabilities at your disposal where you mentioned that this particular container has to leverage only 2 cores of your system or 2 vCPUs of your system in a way. And then from our benchmark exercise, when we mentioned that we could run successfully 176 containers on the ZZ or the Power Systems, all of the containers were evenly distributed. The reason being we say that is our OCP ingress policy was in a way stitched such that it was firing transactions to all of the containers evenly across the systems. So that allowed us to evenly distribute the load across all the containers. So irrespective of where your containers are physically hosted, the load was always equal across the containers. And we could play around by adding more containers or adding more physical servers and assigning those compute capabilities to the containers on the fly. So that's very much possible that we could have, that we have done in fact.
Okay, but then that's your load definition. You have defined your load in a manner where it gets in that it appears even. No comment against what you have claimed, but the definition of the load is like that in this case.
In fact, we have leveraged the policies of OpenShift itself. We have not exclusively defined the load balancing aspect of it. We have just consumed the capabilities which are at our disposal in OpenShift Container Platform. We haven't played with the application loading or the load definition aspect of it. We just deployed it and it was getting evenly distributed across the system.
Yeah, to add to that what Krishna told, right? So there is for each container, how much we can define in the container definition itself, like we see in the deployment config, how much memory and CPU the container should use. There is also something called as the quality of service for each container, which will be defined. So there are different quality of service for each container. So there is something called as best effort. There is something called as burstable. So best effort is something like when you assign 2 vCPUs per a container, it will, even though when you are loading your container more requests, it will not go beyond the assigned CPU or memory, right? So when you define container as burstable, so it will, if there is some processing capability available, even though you have mentioned 2 vCPUs, if there is something available on the system, it will go ahead and it will use that. So you have control to define that in the container definition in OpenShift as well. So that is called as quality of service.
Okay, so this is Argo again. Sorry for interrupting in this conversation. So, I mean, since you are talking about the benchmarking and all the quality of service and all these issues, so my question is a little bit related to this, specific to the Power 9 system. So, do you have any type of benchmarking result where it can show the performance of, like, let's say this SMTs of Power 9, I mean, effect of SMTs on these containers and everything. So is there anything like that? Like, let's say the power of, I mean, performance of OpenShift when SMT8 is enabled, or SMT4 is enabled, or SMT2 is enabled, or it does not really have any impact on the containerization at all?
So that's a wonderful question, sir. So rather, we have done this particular study where we played with different levels of SMT, and we realized that given the nature of the workload where we wanted to scale up the container density, we wanted to host as many containers as possible without breaching the service level agreements that we have defined. We were amazed when we switched between SMT4 to SMT8, and then we realized that we could host a lot of containers in SMT8 mode itself. Given its capability to handle more containers in the SMT8 levels, and then the definition of performing the scalability test with container density was also getting affected eventually. So that's when we saw this particular influence of SNT level there. In fact, I think I'm going to share a URL in the chat where we have published our results on the same aspect of it. And then you could probably take a look at that and reach out to us in a way.
Great, that will be great. Thank you.
Yeah.
Yeah, thank you, Krishna. Thank you, Professor Agya. Okay, we have two more questions from Professor Gopalakrishnan. I know one of them is actually, does our online selling platform uses this type of servers, give some real-time application? That's the first question. Then the second question is, yeah, maybe you can answer the first question, then we can move on to the second one. Krishna?
Okay, so does our online selling platform uses this type of service? So this question is kind of little conceivable. Mithun, do you think we have this kind of service? We do have it, right, in our econfigs?
Yeah. So we do have it. Gopal, when you say online selling platform, you mean to say any of the ERP or any of the other online sellers use these kind of servers, or
let me allow Professor Gopalakrishnan to talk. I'm bringing him on.
Hello.
Yeah, go ahead, sir.
Because this type of servers, to get its most performance, we will have to have that much of scalability and data to handle. We cannot simply buy this server and use it for normal usage. So I want to know how much scalability this type of servers can handle, how much data it can handle, or it is just a processor which does multiple works. Because you are telling a OS sitting on another OS and it is processing. So I wanted to really know how much scalability, in type of scalability, what will be the maximum wherein we can advise that, like for a particular problem, which server I can choose. So you need to know the scalability of this service.
Sure, I think that's a really wonderful question, Gopal Krishna sir. So I think, Mithun, if you could probably bring back your PPT where you have mentioned the IBM Power 9 family, where we have, we know what kind of server caters to what kind of needs. So probably if you can bring back the screen, it will be wonderful.
can you see my screen?
Yes. So we have, we do know that there's no one single server that can cater to all of the needs. And we have to strongly consider the economics of how much we are going to spend for the application study in a way. So coming from the left-hand side of the screen, we have LC922 box, which is Linux cluster, and this is OpenPOWER kind of a server itself, which kind of caters to big data applications, big data and analytics kind of an applications. And we have AC922 class of server, which is particularly fine-tuned to work along with AI, and AI, when I say AI, is broadly mix of ML and DL. And then moving on to the right-hand side of the screen, we have enterprise grade servers, which caters to SAP HANA kind of a workload. And then we have IBM DB2 or the Oracle's database that works wonderful on E9 or enterprise kind of workload. Again, just to circle back to your question, it depends on how you define your solution. So if you want to run your big data kind of a workload, you can very well run it on a C922 box, right? And then this is by definition on how you want to go or what kind of application you would want to work with. And IBM Power Systems, in fact, provides platform for free of cost for 14 days, where you can validate your application and get a feel of how capable power systems are, and then make a call and how do you want to consume the hardware or particular software into your application. So does that answer your question?
Professor Gopal, yeah, Krishna, I think you answered rightly, and also the OpenPOWER consortium also do provide servers, for the people, to run their application and show their solutions and all to the entire world actually. So you can reach us out, in either way from IBM as well as the OpenPOWER way to get access to the servers where you can develop and run your solution and make a good impact, in your research area as well as probably teaching and other stuff too. Any other questions for Krishna, Mithun, Himanshu, and the other panelists actually? Okay, I think let us stop here. I'd like to thank again the presenters for the presentations today. Thank you, Himanshu, Krishna, Arsha, Mithun, and panelist, the Dr. Agya Das from University of Wisconsin, Platteville. And also thanks to all the participants who actually participated in the webinar. And looking forward to meet you all on June 29th workshop from Barcelona Supercomputing Center. It's a workshop. It's basically like a 4 hours to 6 hours workshop. Please do participate. And also we have another upcoming workshop in Italy by Sinica. It is going to be on July 9th, and which I already posted, the details, in our chat window. Please do get it and, register it, as early as possible. And it's going to be a complete packed, the agenda, like a 3 hours to 6 hours workshops. 2 workshops are going to be in next 2 weeks. And thanks again. And I'm closing the webinar now. And have a good day and a good night, and also a great weekend. Thank you.
Thanks, Ganeshan.
Thank you.
Thank you.